Okay, everyone. Hello. My name is Justin Essery. I'm an associate professor of politics and international affairs at Wake Forest University. Welcome to the International Methods Colloquium. The IMC is a periodic online interactive seminar discussion on the application of quantitative statistical methods to the social sciences, sponsored by Wake Forest University and Springer Publishing. This week's speaker is Marc Ratkovic of Princeton University, giving a talk entitled Relaxing Assumptions, Improving Inference, Integrating Machine Learning and Linear Regression. This talk will last about 30 to 40 minutes, after which point we will take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window, and you can ask questions at any time during the talk, but unless it's something very immediate like I can't hear you, we will hold all questions until the end. If you want to be recognized and ask your question with your microphone, just raise your hand using the raise hand button or indicate this in the Q&A text box. Otherwise, I will read your question aloud during the Q&A period. A link to the slides will be available in the webinar chat window so that you can refer to it throughout the presentation. And now I'd like to welcome Marc Ratkovic to the IMC. Marc, welcome.
Hey, thank you, Justin. Thank you for having me. I'd like to welcome everyone who showed up for the talk. So today I'm presenting a paper entitled Relaxing Assumptions, Improving Inference, Integrating Machine Learning and the Linear Regression. So to begin, let's start off with the linear regression. We use it to estimate a marginal effect, a slope coefficient. We use it to adjust for background covariates, and under a set of assumptions that we're familiar with, it allows for standard inference, meaning we can use the coefficient and the standard error to generate p-values and confidence intervals with all the false positive rates and coverage properties that we're used to. The linear regression is just ubiquitous in our field as a means of interacting and looking at our data. Now, the linear regression is known to have several shortcomings. First, every linear model is misspecified. So no one, especially in observational settings, thinks that the regression is actually additive and linear in these covariates. Second, coefficients are biased for causal effects. We'll dig into that a little bit in this talk, but for now, the regression is a correlative tool. It doesn't necessarily return a causal estimate. Last, it fails in the presence of interference. So the question I'm asking here is, can we do better? Now, I'd like to begin just by preemptively answering a bunch of questions that you might have at the end of this talk, and I just want to get the takeaways out to everybody. So running through these, I'll be presenting a method, right? Using your method, can I conduct valid inference using a regression coefficient and standard error without relying on linearity and additivity assumptions in the control variables? Yes. Even in the presence of unspecified interactions, nonlinearities, or interference across observations? Yes. And random effects? Yes. Is the estimate consistent for a causal effect, assuming no omitted confounders, even if the treatment is continuous? Yes and yes. Does it return robust standard errors? Yes. This sounds great. Do I have to code it up? No. The software is available on my GitHub. The link is there. Can the examples from this talk be implemented in a line or two of code with diagnostic figures and statistics already implemented? Yes. Are the conceptual and technical details all that bad? Not really. One of the major dimensions of work on this project was connecting all the ideas that we're about to discuss and linking them directly to what appears in an undergraduate Wooldridge textbook. So all of the ideas are presented and grounded and connected to an undergraduate econometrics textbook. So if there's areas that you are struggling with, I refer you back to the right place there. So continuing to the project itself, the regression has been in our field since at least the early 20th century. And advice on how to specify control variables in a regression is at least several decades old. Methodologists have offered a number of different pieces of advice on how we should put control variables in our regression. Some have said we should include all the relevant covariates, but none of the irrelevant ones, which answers rather than asks our question. Include at most 3 variables, or at least not all of them, or maybe just none of them. Frustration with the regression has caused people to turn to machine learning to help. Neural networks, smoothing splines, non-parametric regression, tree-based methods, and ensemble methods But if for reasons I discussed below, these are useful for prediction and even discovery, but they lead to biased inference if they're not implemented carefully. And I'll return to that point. So what we're going to do is turn towards machine learning for a particular purpose. This is going to involve combining machine learning for the control variables with a regression on the variable of interest. This literature dates back, the first example I could find of it was Bickel 1982. So it dates back to the early 80s, through the 80s and 90s, the theoretical literature. But in the last 5 or 6 years, it's been rebuilt and popularized, rediscovered and built out, given the recent growth in machine learning. That just makes all sorts of estimation techniques that we were unfamiliar with popular and at our fingertips. But again, the idea stays the same. How can we use machine learning for a control specification with regression for inference on a treatment variable of interest? Now, that problem has been, by and large, resolved in the field of econometrics and statistics, but the question still remains, concerns raised by political methodologists still remain. One of them is concerns over unspecified interference. In this case, in the social world, ideas like spillover and interference should be considered the norm, but for the most part, our statistical methods either assume away interference or require the researcher to make specific assumptions about the types of interference. The proposed method is going to learn and adjust for patterns of interference, so you don't have to specify it. The second critique comes from the causal literature talking about treatment effect heterogeneity, are showing that if you don't model heterogeneity in treatment assignment properly, it can bias your results. We'll dig into this a little bit, but the proposed method is going to learn and adjust for this bias. Lastly, while not statistically profound, the software does allow you to incorporate random effects, which is just going to include and extend its utility. So before getting into this, I want to talk about what I like about the regression, right? It does a lot of good things. It's transparent and easy to use with readily available software. The diagnostics are clear, assumptions are clear. Its theoretical properties are well understood, and we can use the output from it for valid inference. The proposed method is going to maintain all of these properties. We're not talking about wholesale rejection of the regression. We're trying to keep the baby. So our target of inference is going to be what's called the marginal effect. And I spelled out the definition here using a textbook definition from Wooldridge. The marginal effect is the average effect of a 1-unit move in a variable of theoretical interest Ti on the predicted value of an outcome Yi after adjusting for background covariance Xi. All right. Theta is the target parameter in that we're trying to conduct inference on it. And we'll say that an estimate theta hat allows for valid inference if the limiting distribution of this z statistic is asymptotically normal. So by valid inference, this is just a way of saying if you construct a p-value from it or a confidence interval from it, it will at least asymptotically have all the properties you expect from these things. We're going to start with the linear regression and depart from it. But first, let's start with the regression itself. When estimating the marginal effect theta, the norm in our field is to turn to the regression, which I've just listed here. And let's go through the different parts of this regression. The nuisance components are parts of the model that we're not interested in, but need to get correct in order to conduct valid inference on theta. In this case, it's the control specification. That's something we care about. We just need to get it right. Similarly with the error distribution, right? The specified components are the model are parts that are assumed by the researcher. That's the linear specification here. The unspecified component is the error distribution. We're actually able to use robust standard errors, heteroscedasticity consistent standard errors, to conduct valid inference on theta without requiring the errors to be normal. So let's stop and think about that for a second. We cannot specify, we can leave a part of the model unspecified and yet still conduct valid inference on theta. We can leave the error distribution unspecified, and we're all familiar with that. My question is the following. Can we carry this further? Can we leave the error distribution unspecified in the control specification? The answer, it turns out, is yes, and it leads us to the partially linear model. The partially linear model given here is partially linear because it's linear in this theta Ti term, but the covariates enter through non-parametric functions f and g. They're not assumed or specified by the researcher. They enter just as they need to enter. Now let's talk about how to work with the partially linear model, and I need to make a primary distinction between feasible and infeasible estimates, infeasible and infeasible models. Now, if f and g were known in the partially linear model, I could just construct estimates f of x and g of x for each observation, and then just put them in as controls in a regression and recover a valid estimate of theta. That would be totally acceptable. The problem is that this model is unfeasible. I don't know what f and g are. So what we need to do is to construct a feasible model, we have to estimate f and g, right? So let's say we do it using random forests. What we can do is estimate f hat and g hat using a random forest, and then construct control variables from those and enter them in this regression. This model is feasible in that it can be constructed from the data. So here, if we knew what f and g were up top, in the infeasible model, we'd recover an efficient, unbiased, valid estimate of theta. What we want to know is how can we construct estimates of f hat and g hat that will accomplish the same? This leads us to the idea of semi-parametric efficiency. An estimate theta hat is semi-parametrically efficient if its estimate from the infeasible model is asymptotically indistinguishable as that from the feasible model. So this means we can construct an estimate or construct covariates f hat and g hat, and then recover an estimate theta hat that is asymptotically indistinguishable as that from the model were f and g known in advance, right? And that's the way this literature will often build this. We can do that, was my first reaction to that. I was a little surprised, but it turns out we can, and let's see how to do it. Let's rearrange some terms. So this first equation here is actually the feasible model, but I centered it on the infeasible model, f and g, and then measured the fluctuations around the infeasible model. So this f hat minus f is a put and take, and so is this g hat minus g. So what we're left with is yi is theta ti plus the infeasible model part, right? Plus this second term, which is composed of covariates f hat minus f and g hat minus g. And if you look at it, you might recognize this as a measurement error problem. We want to include these covariates constructed from f and g, but instead we only have f hat and g hat. So in this case, semi-parametric efficiency boils down to when are these estimation error terms, delta f hat and delta g hat, asymptotically negligible, right? When is this measurement error in f and g something we can safely ignore, at least in the limit? So how does measurement error actually bias an estimate? In two different ways. First, if the measurement error doesn't go to zero asymptotically, then it'll attenuate the results, right? So our first assumption on these error terms is that they go to zero. They need to go to zero uniformly at an n to the 1/4 rate. The details are in the paper. The n to the 1/4 looks technical, but actually it's liberating. It turns out that machine learning methods we're used to, lasso, trees, networks, neural networks, that sort of thing, all can hit this n to the 1/4 rate. So what that means is under this assumption, we can go ahead and estimate f hat and g hat using any sort of machine learning method we're interested in. The second way measurement error can pollute or bias our estimate is if these estimation error terms correlate with the residuals. Okay? So now what can we do to leave these uncorrelated with the residuals? Here we just need to require a little bit of subtlety in how we examine this. For delta f hat to not be, for this term delta f hat I to not be correlated with its error term, notice that f hat is constructed from the data, so it's implicitly a function of that error term. Okay? The way to get around this bias is to use what's called a split sample approach. And the way to do that is to actually estimate f hat off half the data and then turn to the other half of the data to construct these covariates and enter them in the regression. So in this way, we're going to use half the data to model and learn our model of how the controls enter the model. And then we're going to use the other half for data the two aren't going to touch, which is going to guard against the sort of overfitting bias that can emerge. So how do we do that? This is the double machine learning algorithm of Chernozikov et al. Let's split the data in half, say into splits S1 and S2. We're going to learn F hat and G hat using data in S1, our first subsample, and we'll use random forest, say. Then we're going to regress Y minus F hat on T minus G hat using data from S2, so that the model for the controls is learned on half the data, but inference is done on the other half, and those two don't touch. The split sample approach is asymptotically valid, but it raises real concerns over efficiency. We're only using half the data for inference. The double machine learning algorithm adds two advances. First is cross-fitting. It uses S1 to learn the controls and S2 for inference, then swaps the roles. So we end up getting two estimates from every split. Then repeated cross-fitting does cross-fitting over and over and over again a sequence of times and aggregates the results over those multiple cross-fits so that our results aren't being driven by a particular split of the data. This is the double machine learning approach. In the partially linear model, it gives a semi-parametrically efficient estimate. Okay, so what's left to be done? The first advance in this paper is actually adjusting for what I term treatment effect heterogeneity bias. All right. The way to do that is to allow assume each observation has its own effect theta I, its own slope parameter on Ti. Then what we're going to do is write the function y equals Ti theta I plus Fg gamma plus epsilon here. And I'm going to rewrite this Ti theta I as Ti theta plus Ti theta I minus theta. And what you'll notice is that this could be written as the partially linear model with this variable omitted. So when is treatment effect heterogeneity a bias? Well, whenever this omitted variable here induces a bias. I show the analytics in the paper, but there are two cases where this bias is ignorable. The first is when the treatment effect is homogeneous. So if theta I is just theta for every observation, this term zeroes out, I hope pretty clearly. The second one is when the treatment variable is homoscedastic. In that case, the fluctuation of theta I around its mean doesn't correlate with the fluctuation or the magnitude of the random component of the treatment variable, so it will actually lead to unbiased inference. DML, double machine learning, is actually susceptible to this bias, and I'll show you in the simulations. The second contribution of the paper is modeling and learning patterns of interference that the researcher doesn't need to specify. So interference occurs when some part of an observation's outcome may be attributable to the characteristics of other observations. This can be homophily, where observations that are near each other are similar, or heterophily, where observations react to far away observations, right? Dissimilar observations. Existing methods generally require knowing or specifying a form or pattern of interference, which covariates are driving it, whether it's homophily or heterophily. The proposed method learns and adjusts for interference, whether homophily or not, using the data. So you don't have to specify, it will automatically adjust for patterns of interference. Now, I don't want to oversell the interference claims, and I just want to be clear on what sorts of interference can be adjusted for and what cannot. The method learns and adjusts for two types of interference. Interference driven entirely by covariates, it can handle. That's just all pre-treatment. Interference, the effect of one observation's treatment on another observation's outcome can be adjusted for, right? All of that can be learned from the data. The method does not just adjust for three different types of interference. The first is endogenous interference, which is when an observation's outcome is driven by the behavior of some group that includes itself, sometimes called peer effects, and this comes from Mansky 1993. He calls that the reflection problem. Also, if there's simultaneity bias in the treatment variable, so if the treatment's a function of other observations' treatments, we can't account for that. And if the treatment variable is a function of any of the outcomes, we can't account for that. Okay? This is a matter of conceptual clarity on the researcher's part. So with some preliminaries out of the way, I want to present the proposed model and how we go about estimating it and how it works. We're going to extend the partially linear model. Here's the model as it appears in the paper. And I'll confess, I wrote it and looked at it and thought it looked a little foreboding. So I just want to take a moment and sort of go through and look at each of the different elements. The theta ti, f of xi, and g1 of xi terms right at the beginning come directly from the partially linear model. Theta is the parameter of interest, and f and g1 are arbitrary functions of the covariance. The interference terms are the phi y and phi t terms. Notice that the phi y term is a function of the covariance and other observations treatments, and h of y is a set of bandwidth parameters that govern how close two observations need to be in order to impact another one. Phi of t is a function of an observation's own covariance, all the other covariance in the data, and bandwidth parameters for it. Okay. The last term, that g2 of xi, x minus I, v tilde I, that's the treatment effect heteroscedasticity term. This, we're going to model any heteroscedasticity in the treatment model and use that to get rid of the heterogeneity bias. The last element, the A and the B, are simply random effects. This is the model that's being estimated by the software that I'm discussing today. Now, how do we go about estimating this? Recall the double machine learning approach split the data into two different subsamples, learned the control specification on one half and turned to the other half for inference. This method is inherently superior because it splits the data into three subsamples and uses each separate subsample to learn different nuisance components. So we split the data into thirds. In subsample S0, we're going to learn the treatment heteroscedasticity term and the bandwidth. So we're going to estimate interference terms in the treatment heteroscedasticity term. Then what we're going to do is come to that second split of the data and learn the nuisance function. So I'm going to treat the treatment error and the bandwidth as data, right, because I estimated them in the previous one. Turn to the second one and estimate a control vector given the bandwidth and the error terms. Then that control vector is going to be estimated on subsample S1, evaluated on subsample S2, and dropped as a control vector when regressing Y on the treatment. Then we're going to gather that result, crossfit, which means the roles of each of these subsamples are going to be rotated, and then we're going to do that repeatedly. We're going to repeatedly split and then average up. Let's look at this a little bit more closely in terms of the equations to see how these different elements come together. So in subsample S0, which is the first split right here, the entire model is estimated. But what we're going to do is actually only retain these bandwidth parameters, hy and ht, and then our estimate of this error term, v tilde I, right here. We're going to take these three and retain them. Then we're going to come down to this first subsample down here and plug in h hat y, h hat t, and v tilde hat I in here. And then we're going to estimate f, the interference terms, and the random effects. And that's what's happening in subsample S1. In subsample S2, we're going to take all the different control variables we've estimated in S1, put them into this vector that I call U, and enter that U into a regression. And so at this point in S2, I'm just passing along from subsample S1 a vector evaluated on this new data, and it enters as a control variable, a control vector. And it's going to give us a coefficient estimate on theta hat and an estimated standard error. Crossfit, repeat the process, average over it. Okay. Phew. So how does it work? Now I'm offering, I implemented a set of simulation studies, not to show, hey, my method works better than yours, because they're not really complex. It's not a very complex setting. It's to show that existing methods have blind spots in very simple settings. So let me run through the different settings that are available that I present in this simulation. Our baseline model is the outcome is the treatment plus the covariate, first covariate squared plus the error term. And the treatment is generated as x1, the first covariate, plus vi, where epsilon I and vi are both normal 0, 1. Okay? Where do the x's come from? They're just 5 normal covariates generated with a correlation of 0.5. So the baseline model is pretty straightforward. To induce effect heterogeneity, I go ahead and I change this plus in the baseline model to a times in yi equals ti times xi squared. And then I put some homoscedasticity in the treatment model. All right? So the correlation between this xi squared term and the variance here is going to induce treatment effect heterogeneity bias. The last setting, I just add random effects. They're confounders, so there's 50 levels. They're normal, they're standard normal, and I just add them into y in the treatment. All right? The sample size is 1,000, 5 normal covariates. 4 of them are noise. I'm only using 1 of the covariates. The only nonlinearity in this entire setup is an x squared term. And I guess this term in the heteroscedasticity. The data are generated from xi, that covariate vector that I drew, but I gave each method the transformed vector x star I, which is xi1 minus half xi2, and xi2 minus half xi1, that xi3, xi4, xi5. Everything else in this is standard normal. What I want to emphasize with this simulation is that if the promise of machine learning is to learn these sorts of nonlinearities and interactions in the model, it should be able to find a quadratic term and handle random effects. Okay? So let's look at the methods that are assessed in this approach. In this case, there's the proposed method, PLCE, for the partially linear causal effect model. Kernel regularized least squares, a nonparametric regression method. The covariate balancing propensity score for continuous treatments. Double machine learning, which I described above. And generalized random forests, which is similar to double machine learning following a split sample approach, but it has a particular random forest implementation optimized for efficiency. And then I also included least squares just to see how that performs. All right. I saw a question. Oh, Gustavo, I'll get to that question after. Okay, thank you. So let's take a look at the results from the first baseline setting. Okay, and I want to talk about this. So the results are going to take this form. In each of the settings, the true marginal effect is 1, just for visual reasons. And in the case where the outcome is y is ti plus xi squared plus ei, and the treatment is xi plus an error term, everybody pegs the estimates pretty well, right? Everyone falls right around 1. These are box plots for PLCE, GRF, double machine learning, covariate balancing propensity score, kernel regularized least squares, and OLS. We're not just interested in point estimates, though. We're interested in inference. That's why I included this sort of quantile plot as well for a diagnostic. Along the x-axis is the expected coverage from a method, and along the y-axis is its actual coverage. So let me show you how to read this plot. Let's take this x right here, which is right around 82 and a half roughly. And what this is saying is that, this is on the CBPS curve, by the way. If we construct a confidence interval, a 90% confidence interval using the CBPS method, it will contain it will have a coverage rate of 82.5%, which is actually not too bad. So it undercovers a little bit, but it's pretty close. If we have exact coverage, then the results from a method should fall right on this line y equals x here. Methods that fall below this line have undercoverage. What that means is that the 90% confidence interval covers the true value less than 90% of the time. Or over here, the 50% confidence interval covers the true value less than 50% of the time. And if we fall in this lower half, there's systematic undercoverage, which is misleading inference. If we fall above the line, there's overcoverage. So a 90% confidence interval will contain the true value more than 90% of the time, which is valid inference, but it's inefficient. And these results are how we're going to compare and look at the simulation results. Here are the results for the settings we just discussed without interference. In the baseline setting, everyone more or less pegs the point estimate. But if you'll notice, this blue line here is KRLS. It actually systematically undercovers. Its confidence intervals are too narrow. That is an example of what I was discussing earlier, where if you use a single machine learning method to try and conduct valid inference on a single split of the data, it's going to lead to biased inference. And we can see that in these undercoverage rates here. It's not horrible, but this is an example of what I'm talking about. In the next setting, I included random effects just by adding a covariate of dummy variables for all the methods. And what you'll notice is that GRF, double machine learning, CVPS, and KRLS all shrunk and had regular bias with random effects. So their coverage rate over the entire sample are all crunched down on this bottom y-axis is 0. Their actual coverage is close to 0. The partially linear causal effect model, my method, and OLS more or less exactly peg it. OLS pegs it because they just enter as fixed effects, right? It seems to work fine. 1,000 observations with 50 levels is totally fine. When we put treatment effect heterogeneity in, PLC stays roughly where it was. GRF goes from underestimating to overestimating. So does double machine learning and CVPS. KRLS goes from underestimating to actually getting it close to correct. And least squares actually overestimates in the presence of that treatment effect heterogeneity. Looking at coverage, KRLS and the proposed method do reasonably well in terms of coverage of its confidence intervals, whereas the other existing methods undercover to one extent to another. When we put both treatment effect heterogeneity and random effects in it, no one does particularly well, but the proposed method stays pretty close. GRF is back to pretty close, and then we start seeing different patterns and biases, and OLS is just missing again. If we come down over here on the right-hand side to look at the calibration of the confidence intervals, we can see again that the PLCE is at least close to this y equals x line, and actually so is CVPS as well. All right. The proposed method, though, is the only one that's performed reasonably well across these settings, emphasizing that the sort of nonlinearities we find in this, a square term in the variance and a square term in the mean, should be within the realm of the sorts of things that machine learning methods should adjust for. The simulation, there's no chicanery behind these simulations. Next, I want to show how they perform in the presence of interference. So to generate interference covariates, the interference covariants are psi t of I and psi x of I. And the only thing to get from how they're constructed is they're actually weighted average. In the outcome, the interference covariate is a weighted average of everybody else's treatment. And in the treatment model, the interference covariate is a weighted average of everyone else's x squared, okay, where the weights are given by this below. So I generated the data using this interference covariates and then asked all the methods to see how they perform. The results from that scenario show up here. In the case with hold on one second. Embarrassingly, this is the same figure. So I'm going to punt on this for the moment and just tell you that my method performs well and other ones do not. Okay. Continuing along, so those were a set of simulation settings that show that the method performs well in terms of point estimation and coverage in the presence of interference, random effects, and various forms of heteroscedasticity and heterogeneity bias. Next, I want to discuss two applied examples that illustrate the use of the method. The first thing I did with the method, the first example, actually takes experimental data and just shows that the proposed method recovers results close to just least squares and using a difference in means. Why do this? In an experimental setting, we actually know that a regression gives us the right answer. So does a difference in means. And I just wanted to convey that taking the data, slicing it, dicing it, machine learning it, mixing it all up and doing all these fancy things to it does the same as a regression when we know the regression is the right answer. Okay? So here's the result. The data come from Madison Weeks in 2018. The outcome is a disapproval of a hypothetical action taken by a president. And the treatment is whether a conciliatory stance was taken in a hypothetical situation years in the future. What was varied besides the treatment and control was whether the president taking the stance was a hawk or a dove, and what this did to their approval. I'll refer you to the paper. It was actually really, really nice. But for my purposes today, what I want to convey is that the proposed method actually gives very similar results to the difference in means and least squares, where we get an estimate of 11.72 versus 11.98 for the difference in means and OLS. And importantly, the standard errors aren't inflated. They're actually a little narrower. So what this is telling us is that in a setting where the linear regression is the right answer, we recover similar standard errors and point estimates. Looking at the effect on doves, the point estimate is 36.2 and the difference in means is 35.4 and 35.19. Again, reasonably close to this outcome here, with a similar standard error to OLS using covariance. Okay? The takeaway then is that in an experimental setting where we know the regression is right, the proposed method does return estimates close to the regression. The second example I turn to involves a really nice observational study that was using a difference in difference. The setup for it, in the early 2000s, Chicago demolished a set of its public housing units, and they were demolished at random relative to, or at least uncorrelated with variables of concern to social scientists, as if random. What the demolishment of the public housing did was it randomly removed Black residents. The projects were overwhelmingly Black residents. It removed Black residents from neighborhoods in Chicago at random and then put them in different areas throughout the city. Okay, so the author wanted to know if this random removal of Black residents from these neighborhoods actually had an effect on white voting behavior, looking at racial threat. The outcome is change in turnout for the presidential election 2004 to 2000. The demolishment of the projects was between these two. The treatment variable is distance from a demolished project. Now let's stop here and talk about, and I'll explain to you why I picked this example. The methodological work of the day required that this sort of treatment variable be binary in order to conduct a difference in difference estimate or even to estimate a causal effect. This is not to blame the researcher in any way, it's just the methodological standing of the day. But this forced the researcher to actually artificially dichotomize this continuous variable, distance, in a way that that can't actually be theorized. So to give you an idea, it's not the case that 200 meters from a housing project you feel racial threat, but 201 meters you don't, right? There's no way that you theorize that there's this sort of discrete break where you're close and feeling racial threat and far away and not. So this again is not to, I really enjoyed the paper. This is not to diminish the author's contribution. It's to say that the author was forced into awkwardly dichotomizing a continuous treatment variable due to the standards of the day. The proposed method actually returns a causal effect for this continuous variable. So we can just drop it in and run it. The controls that are included, 1998 and 1996 turnout, gender, age and squared age, median income for the census block, the value of the dwelling place, the deed for the residence, whether the deed for the residence in the name of the voter, and I also add in random effects by the closest housing project, just a random effect per housing project. The identification strategy pursued by the author, again, is a difference in difference using distance and meters dichotomized. The author was aware that this dichotomization was actually unnatural. So what he did was just dichotomize at multiple different settings and multiple distances and showed that the effect was more or less the same regardless of these distances, right? That's fine in that it persuades that the results are true, but I hope you can see the awkwardness in this. The proposed method returns results that look like this, again, just with a line or two of code. And what we can do is we can say for whites less than 1 kilometer from the demolished projects, we find a significant effect where The further away from the projects, the more racial threat, the more like the larger the causal effect. For blacks less than a kilometer from the demolished projects, and recall that the idea here is to find racial threat, so we should find it in white voters, but not black voters, and that's actually what we find. Blacks less than a kilometer from the demolished projects, there's no change in voting behavior, both substantively and statistically. For white voters greater than a kilometer from any projects where there should be no racial threat under the author's conceptualization, this number turns out to be statistically significant, but it's just tiny. And similarly for black citizens greater than a kilometer from any projects, that number is as close to zero as I've seen any number come out of an estimation procedure. So in conclusion, the method provides an alternative to linear regression. We're relaxing linearity assumptions, adjusting for covariates using machine learning, but we're also adjusting for treatment effect heterogeneity and treatment heterogeneity, which is going to allow us to estimate a causal effect even with continuous treatments. It's going to allow for interference and allow for standard inference on a treatment effect, and it outperforms several existing cutting-edge methods. I'd like to thank Justin for the opportunity to give this presentation. I want to thank everyone for listening so far. I'm looking forward to your questions. Thank you.
Okay, everyone. Thank you for the presentation, Marc. I assume everyone hear me, right? Yeah, okay, good. I was got to make sure I clicked all the right buttons. At this point, we can take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. You may also click the raise hand button or indicate in the Q&A text box if you would like to be recognized to ask your question via audio. And we did have one question that came in during your talks, and so I think we'll just start there. Gustavo Diaz asked, can you say a bit more about why the proposed method cannot accommodate for other kinds of interference?
Absolutely, thank you. Let me go find the correct slide so that we can talk about this. Okay, thank you. Thank you, Gustavo. Excellent question. I appreciate the opportunity to clarify. The first part of my answer is there's much more on this in the manuscript and the appendix, so I encourage everyone to go read the paper. But to address your particular question, the method can be thought of in the same terms as a regression, okay? What it can't handle are cases where the outcome variable shows up on the left-hand side and the right-hand side. No regression can handle that without actually modeling both sides using some sort of formal model or some kind of assumptions. But if the error term is on both the left-hand, if the outcome is on both the left-hand or the right-hand side, the model can't handle that. So that's what endogenous interference is. What that means is, let's say that my outcome is an average of what Justin does, what I do, and what you do, right? And let's talk about, smoking. I quit 7 years ago, but let's say I'm reconsidering, right? So I look at my peer group of you and Justin, and I see that you guys don't, and I say, you know what, I'm not going to do that. And then what I'm doing is I'm making my outcome an average of my peer group's outcome, but my peer group's outcome is a function of my outcome because you guys are looking at me and doing the same thing. And that sort of simultaneity bias can't be adjusted for in a regression without many further assumptions and basically formally outlining how that happens. Simultaneity bias in the treatment variable, we can't account for that for exactly the same reason. And then outcomes affecting the treatment variable, that's a problem of reverse causality, right? That's confusing the left and right-hand side variables. The y variable needs to be on the left-hand side, not the right-hand side. Did that address the three concerns? Please let me know if any of that was unclear or could be further elucidated.
While Gustavo is thinking about that, I'll go ahead and ask a different question, and we can come back to that if he has further questions. So one thing I was thinking of when I was looking at the structure of your model is, according to Pearl, you definitely don't want to control for a collider, right? You don't want to control for something that X causes and that Y also causes, because if you control for that, it creates this spurious relationship. And in your model, in the ML part of your model, I should say, there's no
Yep.
causality. It's all about essentially a relationship. And so
Yep.
if there's a collider in the set of X that's in the model, is it going to put it in there and create some sort of problem?
Yes. Let me distinguish between the sorts of assumptions we need to make about our model and what the machine learning methods can learn, right? Machine learning methods can't learn causal patterns. There's some work on that. I don't want to overstate that. But
Yeah,
those
there's the
methods,
Bayesian network stuff, but it
yeah, but
really kind of works.
I don't want, yeah. Can we just leave it at it kind of works?
Yeah.
Okay. So what we can't do is say, here's a bunch of covariates, find the colliders and don't include them. I'm assuming
Right.
that's been done by the researcher. And I didn't get into that in this talk. The assumptions are written so that in the details and the assumptions, they're not included in the set of allowable covariates. So like analytically, I'm safe, right? I ruled those out.
Mm-hmm.
But in terms of what you're saying, I completely agree that that can be brought forward, and saying things like collider variables, post-treatment variables, those sorts of things need to be ruled out ex ante by the researcher, because including them in my fancy non-parametric regression will induce the same sorts of biases for the same sorts of reasons they would in incorporating it in a standard linear regression. And in fact, one of the appeals and the reason I've developed this method to be so close to a regression just with like non-parametric parts to it is that all these biases port over. So if you say, hey, I can't include a collider in a regression, then you shouldn't put it in this.
Okay.
Right? And it carries through for the same reasons.
And I assume, just to make the point pretty, this is probably already obvious, but if you don't put in all the right, if you don't have a complete set of confounders, if you've left one out, this is not somehow going to magically fix that either.
Agreed. Now, I will say, and I didn't talk about this in the talk, I'm relying on the excellent SenseMaker package by Sinelli and Hazlitt. It's just really fantastic. And they can go through and actually characterize sensitivity analyses on how large does a confounder have to be to turn your results upside down.
Right.
The major advantage of this approach over the random forests and the double machine learning is at the end of the day, in my third split sample, I have a regression. Mm-hmm. And since I have a regression, I can conduct regression diagnostics because I know what those are, right? So all those sorts of diagnostics, I mean, I didn't put it in, but if someone wants Cook's distance in there, I could put Cook's distance in there. Why not, right? Like all those, at the end of the day, given what I do in the first two splits, subsamples, the third sample is a regression, so I can just do all the same stuff we're familiar with.
And so I want to compare. I know this is not necessarily like, oh, why is your method better than this other method? But when I think about matching, particularly coarsened exact matching or other variants of exact matching, what they're trying to do in principle is sort of reestablish the logic of a random assignment to treatment, right?
Yep.
And that's also sort of, in a sense, what you're trying to do, right? You're trying to correct for these imbalances that are created by non-random assignment. So what is the theoretical or logical advantage to using this method as opposed to just doing coarsened exact matching?
It's subtle, but thank you for the opportunity to answer that question. Coarsened exact matching mean adjusts, right? Because you get the boxes and it's just going to mean adjust.
Yep.
A lot of this literature was developed with a binary treatment variable where mean adjustment is sufficient, literally statistically sufficient, right? It's sufficient to characterize the whole treatment distribution. Mm-hmm. But to properly adjust for the treatment variable, you actually need to mean and variance adjust because we want to get the first two moments correct. Coarsened exact matching doesn't variance adjust. It only mean adjusts. With a binary treatment, that doesn't matter, right? If the mean is p, the variance is p times 1 minus p. So one determines the other. But with a normal or a continuous treatment variable, that can actually matter. Mm-hmm. So one of the insights of the paper and one of the hard parts of pushing it past the binary treatment was also adjusting for the variance of the treatment so we could get the first two moments correct.
And of course, you can force a continuous treatment back into the CEM box, but that's sort of what you were talking about with the Enos paper, right?
Yeah, you can go one way, but not the other. You can always coarsen things, but why should, like as methodologists, why should we have people doing such ugly things to their data? Without picking on Ryan Enos at all. It's a fantastic paper. I picked it actually because I did like it.
Yeah, it's not about him. It's more his paper. It's
No,
about the
it's
general.
about forcing people to like dichotomize variables when they shouldn't have to.
And this also might be obvious, but thinking about the connection between your model and like the sort of Neyman Rubin causal inference assumptions, I assume it's partially about solving the sort of no over I forget what it's called right now.
Sutva?
Sattva, yes.
Yeah.
It partially addresses Sattva, but it's mostly about the independence assumption, the independence of treatment and causal outcome. Is that right?
Yes. So it does deal with Sutva in the non-interference part, right? And which is that's the key thing in Sutva, that you can actually relax.
Right.
The strong ignorability assumption, which is another part of that world that we discussed, and I go through this in the paper in some detail and more so in the appendix, is that existing methods require that there's a set of observation level covariates that can break confounding in the presence of interference that might not be the case. Mm-hmm. So we can relax it from there's a set of observation level covariates that can break confounding to there's a set of covariates in the sample that can break confounding. And that's the major contribution analytically. It turns out writing that down analytically is easy. I just put like other things on the other side of the condition box.
Right.
Coding it up and setting it up so that you don't have to specify the interference was the hard part. So if there is geographic interference, it'll learn from latitude and longitude what it was. But if the latitude longitude interference varies by age, it'll pull that in too. You don't have to specify the precise nature of the interference.
So I'm just going to ask one more question, and this is sort of harking back to old school methodology papers, where an important part of advocating for some people to use some new method is showing that, hey, if you use the standard techniques on this problem, you get one answer, but if you use this other technique, you get a different answer, and that difference is really substantively meaningful. So the two examples you have in the paper, one of them sort of verifies that it works. It's supposed to be the same. The other one, it's still pretty much in this. You lose some information with the old approach, but it's still basically fine. Have you come across any examples where this really makes a difference?
Yes. Part of that was not trying to pick a fight in the review process. I will freely
believe me, I understand.
What I found, and I'd be glad to discuss more of this offline, because we're just, for time reasons.
Yeah, we're a couple minutes left.
Is that in our top journals, we're not publishing bad regressions. They're theoretically motivated, they're well-grounded. And what I wanted to convey in the simulations is the linear regression kind of works. It's at least as good as option as all these other machine learning things. It's not a bad option, right? Gauss and Markov were onto something. But in regards to your question, I found the major change comes from the standard errors, not the point estimates. So when I go through and replicate things, it's not that the modeling assumptions are giving me changes in bias, they're shrinking our standard errors. So I have found results in APSR and AGPS. I've replicated 15 or 20 different papers with this that flash out of significance. The point estimate more or less stays the same because we all kind of know what the point estimate should be, and the review process stops us from publishing ludicrously wrong coefficients. Where it really comes in is from thinking through uncertainty better. And the standard errors from this method, if it's linear, the standard errors are the same as the linear regression. But if there's non-linearities, those standard errors will inflate to accommodate that. So that's the major change.
Well, as you mentioned, we're about out of time. So I'm going to thank Marc for being our presenter this week. I want to remind everyone that this talk will be posted to our website so that you can share it with a colleague or watch it again later. I also want to announce a talk on March 11th. That's not next week, but the week after, by Dawson Figueiredo of the University. Boy, my Portuguese is terrible. Universidade Federal de Pernambuco, but he's currently at Oxford. I can pronounce that one. So check our website, www.methods-colloquium.com, to get more information about his talk in 2 weeks. And Marc, thanks very much for being here today.
Thank you for the opportunity. And thank everyone for participating.
And I hope to see you all next week or 2 weeks from now. 2 weeks from now.